Alright, thanks for watching. And today I would like to prove a very nice property of determinants that is called multilinearity. Because even though the determinant is not a linear transformation, the determinant has a nice property that in each row it is a linear transformation. And so just a couple of definitions. First of all, if I write something like that, A1 up to AN, this is the determinant of the matrix whose rows are A1 and up to AN. A1 dot 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 AN. So just to illustrate, for example, in the case n equals 2, if A1 it's, let's say, 1, 2, and A2 is 3, 4, then the determinant of A1, A2, it's the determinant of 1, 2, 3, 4, which if you want is minus 2 in this case. And what I want to show is the following. So fact, multilinearity. So if you just fix yourself on one row and ignore all the other rows, then the determinant is linear in that row. So fact, multilinearity. Namely, for all r equals 1 up to n, if you again take the determinant of the matrix with A1 up to AN, but the rth row it's of the form u plus kv. U and v are vectors, k is a constant, then it's a determinant of A1 up to u, AN, plus k times A1 up to v and AN. So if you want, just to simplify, so in the case n equals 2, and r equals, let's say in the case r equals 1, all this says is that u plus kv, a2, it's linear in this row, so it's u a2 plus k v a2, and if you want in the case r equals 2, this says that a1 u plus kv, it's a1u plus k A1v. So it is indeed linear in each row, even though itself it's not a linear transformation. And this seems like a silly property, but it's so important. It's the thing that makes determinants work. And in fact, all the other properties I show in other videos, they all rely on this multilinear property. Alright, and so let me show this. So why? I guess proof. First of all, and you'll see why this is convenient, the case r equals 1, we can just do it directly. So check r equals 1. And by the way, so I forgot to say, so far, we only know that we can expand out the determinant along the first row. So this is not quite an obvious property. It would be obvious if you could expand it along the rth row. But since we don't know that, we have to do some work. Okay, so now, what is the case r equals 1? So what this means is, let's see. What this means is that A is of the following form. A is of the form, let's say, U1 plus K V1, U2 plus K V2, dot dot dot, UN plus K Vn, and then other terms, A21, A22, dot dot dot, A2n, until the last one, ANN, A11 up to ANN. And again, this is if you want the row U plus KV, A2 up to AN. happens if you evaluate that determinant along the first row? And you know you can do this. Not because I believe in you, just because that's just the way the determinant is defined, up to expansion along the first row. Then what is the determinant of A? So you want to take the first row and sum over all the columns. So sum from j equals 1 to n. And remember how the determinant is defined? You have a bunch of pluses and minuses. And here you start with the first entry. So plus is minus 1 to the 1 plus 1. And then minus 1 to the 1 plus 2. Up to minus 1 to the 1 plus n. This is the perfect way of describing plus, minus, etc., etc. So minus 1 to the 1 plus j. And then you want to take the jth entry, which here is uj plus k vj. And then the determinant of the rest, which you usually write it, if this is like a1j, the subdeterminant is the determinant of what's called a1j squiggle. A1j squiggles just says, suppose you Bomberman this thing and you consider the determinant of the rest, the rest is the submatrix. Okay, but then that's not a big deal because now we can just use distributivity. So those are all scalars. So you can just write it as follows. So now just distribute everything. So this is a sum from j equals 1 to n of minus 1, 1 plus j, uj, subdeterminant, and then just distribute, again it's a finite sum, so k times sum from j from 1 to n of minus 1 to the 1 plus j, vj, subdeterminant. But what is this? It's precisely the same thing as the determinant of the matrix u1, un, a21, a to n, and then an1 up to ann. Because how do you find the determinant of this matrix? You do minus 1 to the 1 plus j. You take this entry here, let's say uj, and take the subdeterminant, which is the same as the subdeterminant here. And therefore, this thing is precisely equal to the determinant of the matrix with rows u, a2 up to an, and plus, same thing with v, so k times v times the matrix of a2 up to an. And what was this? I forgot to say. That was precisely a matrix with rows u plus kv, a2 up to an. So with this long line, I've shown the case where u plus kv is in the first row. And as I said, this one was not too bad because we know we can expand determinants along the first row. What is slightly trickier is to do the case where you have a different row, because we don't know yet that we can expand determinants along a different row. So in order to do this, we have to use a bit of induction. So just a sprinkle of induction, as is usual with those determinant proofs. So now let's do induction on n. N, which is the size of our matrix. So suppose if A is n by n and R is from 1 up to n, then the result is true. You know, A1 u plus kv an, it's A1 u an plus k a1 v an. then, sorry, I mean, let Pn be this proposition. So, be the prop. Then it all starts with the base. So the base case, well, let's be lazy. Let's just pick the case n equals 1. Then it's kind of silly because, first of all, there would just be one row, which if you want, we've also shown. But in this case, we would have a 1 by 1 matrix with just one entry, which is just a scalar. Then determinant of u plus kv, okay, that's just because it's a scalar, it's u plus kv, which is the determinant of u plus the determinant plus k times the determinant of v. So the base case is not a problem. So now for the inductive step. Suppose this is true for n minus 1 and times n minus 1 matrices. Matrices. Show that it's true for n by n matrices. All right, so again, suppose A is n by n, and let R be 1 up to n. Let R, if you want, be given. One little thing, and you'll see why we need this. We've already shown the case R equals 1 separately. So let's just do the case R is greater or equal to 2. Because we would like our first row to be just like A. All right, now, we just need a little bit of notation because it turns out when we expand, when we take a subdeterminant, we're eliminating an entire column. So in particular, take the vectors and eliminate each entry of that vector. So just a little notation. For J fixed, okay, and X, if you want, be in Fn, X hat is just X, but with the Jth entry removed. And again, technically this hat has to depend on J, but let's just to simplify notation, assume this J is gone. So for example, suppose n equals 4 and X, I don't know, it's 2, 4, 6, 8, and J equals 3. If we remove the third entry from X, it just becomes 2, 4, 8. Let's just eliminate this. All right, why is that useful? So, suppose you have an n by n matrix, and you know one of the rows is of the form u plus kv. So A is of the form, if you want determinant of A is a form determinant of A1. Again, there's no R in the first entry, and then let's say u plus kv. Up to an. All right, then what does A look like? A looks like, A11, A1n, and in general A1j. And then we have stuff like U1 plus KV1, UJ plus KVJ, UN plus KVN, and then AN1 up to ANJ and ANN. All right, first of all, if we expand out the determinant along the first row, which is the only thing we can do so far, we have to wait, I think next video or stuff we can do it along any row. then by definition, this is the sum from j from 1 to infinity. So funny, I've taught calculus way too many times. I automatically say sum from 1 to infinity. Well, no, sum from 1 to n of minus 1 to the 1 plus j. And then notice, because we assumed that rho was bigger than 1, those entries are purely entries from A, like entries from A1. So you can legitimately say A1j and the subdeterminant. Now, how do we obtain that subdeterminant? First of all, you eliminate the first row, right? That's one thing. And also, this is why I introduced that notation. In that column, you eliminate the jth entry from every column. So if this is A2, U plus KV, and then AN, what this becomes is the sum from j from 1 to n of minus 1, 1 plus j, A1j of the subdeterminant of the form A2, and then, which might be U plus KV, and not quite A2. So A2, but with the jth entry removed. So A2 hat, and then U plus KV hat, which if you want is just U with the jth entry removed, plus KV with the j entry removed. U hat plus KV hat up to AN hat. All right, and again, I think, okay, never mind. All right, now, what's the point? The point is, notice, this matrix, first of all, it has one row less. Okay. It has one row less, and therefore also a column less, so it's of the form n minus 1 times n minus 1. But not only that, notice it has the same form. It is of the form some row, some row, some row, and some row of the form U plus K something else. So in fact, it's an n minus 1 times n minus 1 matrix of the same form. And in particular now, we can apply our inductive hypothesis, which says that it's just of the form sum from j equals 1 to n of minus 1, 1 plus j, A1j of, the determinant of A2 hat, U hat, AN hat, plus, again, just distributing sum from j from 1 to n of minus 1 to the 1 plus j, A1j, the same thing but with V. And by the way, so it's possible, of course, that A2 hat will be of the form U plus KV hat. So I guess you can use induction or just the case R equals 1. So that's all right. And by the way, so we made sure that we excluded the case R equals 1 because otherwise we wouldn't have a matrix of that form. We wouldn't have like U hat plus KV hat. All right, and I forgot the K. All right, and then basically if you reverse this process, what is A2 hat, U hat up to AN hat, it's precisely the determinant of, this whole thing, if you just reverse engineer it, it's precisely the determinant of A1, A2 up to U up to AN plus K times A1 up to V up to AN. The reason is, it's just the reverse of this. How do you evaluate that determinant, which is again A11 up to A1j, A1 A1n, and then U1 up to Uj. It's huge. Up to Un, and An1 up to Anj, and then Ann. Well, how do you evaluate the determinant? We still have -1 to the 1 plus j, A1j, and then, again, you remove the first row, and you just remove the jth entry of all the remaining rows, and you get precisely this formula. So indeed, we are done. We have shown multilinearity. And next time I will show why this is so important, because it helps us with two things. First of all, it helps us show that determinants are independent of the row you choose, okay, to expand this on, and also stuff like how later on it's proved to show that the determinant of AB is determinant of A times determinant of B. Alright, I hope you like this determinant extravaganza. If you want to see more math, please make sure to subscribe to my channel and please ring the notification bell. Thank you.